thank you very much for the introduction. And first of all, please excuse me for my voice. I tested, it's not COVID, don't worry. The track is about plug-and-play integration for robots, development, manufacturing, and QC. And my talk will be focusing on a reference architecture model, which we believe will make this easier for users and integrators. So let me walk you through the presentation. I will first talk about the challenges of robotized automation systems in laboratories, and then introduce the framework which we call laboratory automation plug-and-play, and its various aspects, including a hierarchical decomposition of the laboratory workflows, especially focusing on the pick-and-place labware transportation, outlining a framework for information representation that enables plug-and-play teaching for integration of lab robots, again focusing on pick-and-place, and especially focusing on representing the positions, so the geometrical relations, the teaching points basically for robots. We also outline the layers of the control pyramid and distinguish between the boundaries, and also find the corresponding layers of the decomposition that got represented in the control pyramid. Finally, I will present proof of concept studies, both outside and inside of Takeda. So let me start by a general introduction. Laboratory automation poses a bit different requirements than traditional high-throughput automation. So there we have a more dynamic environment. We have modular processes and we need the flexibility. We have to connect standalone unit operations, standalone devices, and humans often need to be kept in the loop. So that's where collaborative and mobile robotics comes in handy. They can operate in human-designed environments and interface with modular equipment. Also, for us, especially interesting in how these robots can collaborate and cooperate with humans. So for that, I created a table that summarizes the strengths and weaknesses of each approach. Of course, stationary robot is the highest throughput available. It has high availability, but relatively low flexibility. A mobile manipulator is in the middle ground in terms of availability. So it's strange that we know humans are still, as the current state of the technology, faster than mobile manipulators. But where they shine, where MOMAs shine, is availability. So they can implement 24/7 operation, they can work at night and during the weekend. That's why multiple solution providers have already launched their mobile manipulators, primarily for pick-and-place sample transportation of standardized labware from predefined positions between devices and laboratory components. And these mostly share the same anatomy. So they have a mobile base capable of simultaneous localization and mapping down to the centimeter accuracy. They have robot arms from 4 to 6 degrees of freedom, and to counter the inaccuracy of the base, they need an additional means of positioning, either with vision or with a mechanical touching probe. They have parallel grippers for the previously mentioned standardized labware, and the challenge is that they represent a highly complex system by themselves. We will see that they compose of several layers, many interconnected components, and of course many sources of errors. So to simplify how these are integrated, we created a conceptual framework that we call the laboratory automation plug-and-play concept. And the first aspect of that is to decompose the lab workflow, starting from the very high level, the set of services that the laboratory provides. And those consist of experiments or assays, And there, it's important to mention that this outline utilizes the notion of subordinate activities composing a higher level activity. So an assay is consisting of tasks, and tasks consist of subtasks. So here we outline examples for liquid handling, and which we will especially focus on, lab work transfer. And there we see that subtasks are implemented by the means of motion sequences, so trajectories that the robot arm completes. And those can further be broken down into motion primitives and ultimately actuator primitives. So this we outlined in a graphical representation. Bear with me, I will walk you through. Robots need self-sustaining functionalities. So that's why we created the maintenance category or namespace, you can call it. There you see, for example, battery status monitoring and going to the charging station if needed. And also some solution providers may want to expose their teaching interface towards the scheduler or the laboratory automation interface. The next most important category is an outcome-oriented category, still fairly high level, so task level and subtask level. This is for lab work transfer. And there you see that it consists of a bunch of subtasks, picking and placing the labware, and also some prepare actions. The arrows represent composition, and I will explain why we have horizontal lines also later. The low-level category is something that not every solution provider might wish to expose towards the lab automation system. So these are implemented on the robotic system level. And I will show the elements of the control architecture. There we divide the activities based on the component of the mobile manipulator. So the base, the arm, and the gripper. And for each you can see the motion sequences analogous to each other. For the base we have driving through a sequence, docking and undocking. Whereas for the arm controller we have moving through a trajectory or a sequence of motions. The gripper can also be controlled either by position or force control. And you see how it's all broken down further into motion primitives and actuator primitives. So each activity has its own set of parameters, which the control system might use to trigger and parameterize the actions. So I will walk you through a decomposition of the pick and place lab work transfer activity. And again, bear with me, this will be a pseudocode representation. I will later walk you through one by one. Here the indentation represents the level of activity, and also the coloring is there to help us. We used asterisks to mark activities that are specific to mobile manipulation. So the basic principle is that we need a representation which is agnostic towards stationary and mobile robots, all the way down to the subtask level. Below that, there will be differences, you will see. So this is just to provide an overview, and I will break it down. There you also see the parameters and then the breakdown. First, I would like to introduce another aspect of the framework, information representation in the form of ontologies, primarily for the pick and place application. And there we need an ontology of labware, so the workpieces that the robot manipulates. And the labware also needs to be interfaced with by the liquid handler, but now we focus on manipulation, so external manipulation. And for that, we need the gripping height, we need dimensions, we need force tolerances and parameters like that. But primarily, again, the position representation relative to the zero coordinate system. So for the well-known SBS microplate, we define a central coordinate system, and in relation to that, you can define the valve positions and the gripping frame. So there is an endeavor ongoing as a collaboration of the SILA Robotics Working Group and the Bits in Bio group. This endeavor is led by Mark Durr. He created a stack where the EMMO-based ontology is used and implemented in terms of web ontology language in Python classes. Very important, we will see later, means to query the database by SILA commands. So the next step is to use the same approach, the same framework, and create a similar ontology for devices. And there, again, we need to represent the positions, the teaching points, basically, for the robot with relation to a device coordinate system and by considering the position of the marker, either optical or physical touch marker. So in the next slide, we will see how the coordinate systems are defined by the means of a series of coordinate transformations relative to each other. And on the device's front side, there always needs to be a marker. And with relation to that, you have the handover site. And with relation to that, we also define a sequence, an approach sequence. So the robot localizes itself by simultaneous localization and mapping, and also tracks its own configuration by the means of kinematics. And in terms of optical markers, it uses a camera system to bind its own frame to the device's frame, basically. Now, within the device, the relative positions, according to this concept, are represented in the ontology or digital twin of the device. So when the robot docks to the first station, it needs to use marker detection, and only then can it plan the motions so that the relative positions can be connected in a more accurate way than what's provided by simultaneous localization and mapping. So here you see that the components of the system are outlined. The room itself has its own digital twin instance, the robot has its own digital twin instance, and the device has its own. And they are all connected within this framework by the means of coordinate transformations. So when the robot detects the marker, then on the top you see the previously mentioned activity representations. So then the pick action is initiated, and a move sequence makes the robot to approach the handover site, and then it picks the labware. So then the labware is in the tool center point of the gripper. It needs to put it on the onboard storage, the hotel, navigate to the next station, then pick the labware again from the storage, and again, before placing it, it needs marker detection with the camera to bind its frame to the next device's coordinates. Then it plans the motion for the approach and places the labware on the destination device's appropriate site. So how it's implemented in terms of control pyramid, we use the same 7 levels and corresponding to the previously mentioned workflow decomposition. On the very top, we have lab management systems, so LIMS or ELN. And then what's most interesting in terms of laboratory automation, the scheduler or laboratory execution system. That's where the procedure, the experiment is programmed as a series of tasks. So again, we have the breakdown of the workflow, and then the tasks themselves are implemented on the level of devices, including robots, mobile robots also. Subtasks and motion sequences are further broken down, and there, later we will see how the boundary can actually shift. So motion sequences can either be implemented on the device level control, dedicated PC, or on the embedded controller. But in most cases, the motion primitives and actuator primitives are, in fact, implemented on the embedded controller. So in a laboratory, you, in most cases, have a bunch of different devices, standalone. You want to connect them. And for that, you need a scheduler on top, a master controller or laboratory execution system. And for physically connecting the devices, you need robots. Here we will present the mobile manipulator. And as I mentioned in the beginning, those consist of multiple different components by themselves. They also have a built-in control unit implementing the interface and the control of the hardware. And you may have a bunch of these robots making up a fleet. So you need to control the fleet itself. And there you need a middleware layer, a so-called fleet manager that sits between the robots and the scheduler. And the scheduler ultimately only controls the task and subtask level activities by the means of high-level commands. And then how it's broken down, you can also observe the previously mentioned layers. So how we implement it, let me introduce a few proof of concept studies. First, the SILA hackathon, the BioSesh hackathon, where we implemented the concept for two different robots, the universal robot and the precise flex, each having their own hardware and embedded controller layer. And on top, for us, the most interesting part was to implement a bridge on the device level control, so on the PC level. And of course, the whole system was controlled by a scheduler by the means of SILA commands, as interpreted as subtasks. So here we see that there is a difference between what level of activity is communicated between the device level control and the embedded controller. So the universal robot, we implemented the motion sequences on the embedded controller, and the bridge only triggered these motion sequences. Whereas for the precise flex, the sequence was implemented on the device level control, and the motion primitives were triggered one by one on the embedded controller and only interpreted there. A similar approach we will use for another proof of concept study, which we are conducting, Takeda is conducting together with the Óbuda University in Hungary. The Tiago mobile manipulator, which is a ROS-based research platform, will be used. And there, a SILA server, a SILA bridge will be implemented again. And most importantly, we will implement the previously mentioned information representation framework, the ontologies, and make sure that the master computer, the master controller, can fetch the positions from the ontology by the means of SILA queries. And of course, on the top, we will have a scheduler. So at Takeda, we have a network for collaboration on this topic. Together with solution providers, we are making sure that we implement these concepts within the bounds of pharmaceutical sciences, which is a part of R&D, but we also collaborate with global manufacturing and supply and global quality. Two of my colleagues, David Walton and Anna-Marie Hasenbichler, will talk about a few of those applications later down the schedule. For us, also very important are academic collaborations to be the cutting edge of these technologies, and organizations and forums like SILA and ISPE and BPOG. So this diagram I have already shown on a conceptual level. Here I just wanted to outline that at Takeda we have a series of selected components and partners to implement it. We will implement a global proof of concept study at 3 sites globally in Lexington, USA, in Austria, and in Japan. Each time with an Omron-based mobile manipulator and a BioZero scheduler, and very important, a SILA-based communication. So finally, I want to show the animation of the previously mentioned simple pick-and-place demo, nothing fancy. The first stage will be to just perform it on the bench and then connect the devices. The robot needs to locate the positions, and that you will see in the next video, which is a bit more fancy. Here, the robot will interact with a storage unit. And you will see that it first has to locate the handover site by scanning the optical marker, load the labware, and then navigate to the next target, which will be a station for swapping the gripper. So that's also something that we will test, how the robot can use a tool changer to be able to manipulate different types of labware, microteeter plates and petri dishes in this case. So finally, I would like to thank all of my colleagues at the Obode University, at Takeda, and at SILA, and of course, our partners. And if you're interested, you can check out the public project website. There we have all of the public material that we have presented and published so far. So thank you very much for your attention, and I'm looking forward to your questions.
Yeah, so I think we have time for about 1 or 2 questions. So if anyone have any questions currently?
I have a question.
Yep.
Yeah. Hi, I'm Maria from Novo Nordisk. How long time did this take you? When did you start?
The conceptualization, we started actually in 2019. Then we implemented the first proof of concept study and then a simulation-based study for marker-based manipulation. And then progressively we created the conceptual framework for decomposing the workflow, for outlining the information models. And now we are starting to implement aspects of this concept in terms of proof of concept studies.
Okay, thank you very much.
Thank you.
Yeah, I think we have time for 1 more question, and then feel free to meet Adam outside for any additional questions as well.
Hi, I'm Bilal from ABB. I have a question. Like, what were the biggest 1 or 2 challenges in order? What were your findings out of it? Yeah, thank you.
Thank you. So I think the biggest challenge is accuracy and errors, of course, in the process. So the marker detection is the bottleneck. We will have to assess the reliability and accuracy of that step. And of course, the digital twin will need to be able to accommodate corrections and calibrations, mechanical deviations, and also systematic errors of the metrology system. So that's something that we will have to assess on the long term. Thanks.
Brilliant. Brilliant. Thank you very much, Adam. Again, we have to move on to our next presentation, but Adam will be around